Chinese researchers have cracked the secrets of the strawberry family of models. That is the OpenAI O1 and O3. These are the cutting edge thinking models, which many are classifying as AGI. Test time compute is what makes O1 and O3 so powerful. It is what allows it to reach PhD level mathematics and scientific research. But here's the thing. OpenAI and only recently Google are the only two companies who have really cracked the code to these thinking models. Until now. This research paper explains exactly how to reproduce the thinking aspect of these models, test time compute. And their goal? Crack the secrets of test time compute and open source it. They discovered the 4 critical elements to how it works. But first, let me break down the basics. So here's the research paper. It is out of Fudan University and Shanghai AI Laboratory, and they literally go over every possible aspect in reproducing the O1 model. If you're not familiar with the O1 and O3 models by OpenAI or the Gemini thinking model by Google, they are essentially large language models with the ability to think during inference time. What does that mean? That means when you submit a prompt, it doesn't just respond with the first thing it comes up with. It takes its time and it thinks. It uses many more tokens and much more compute during this prompt and inference time. And the result? Insane performance on really complex tasks. Math, science, reasoning, logic. These models, especially O3, we've seen beat the vast majority of people on Earth at mathematics and coding competitions and basically everything. And before I read it, I want to just say the only model that they mention is the O1 model because this research paper was being authored prior to the O3 model coming out, but the O3 model is essentially the same thing as the O1 model, just better. OpenAI O1 represents a significant milestone in AI, which can generate very long reasoning process and conduct human-like reasoning actions like clarifying and decomposing questions, reflecting and correcting previous mistakes, exploring new solutions when encountering failure modes. The O1 model dramatically transcended the reasoning capabilities of preceding LLMs, achieving performance comparable to PhD level proficiency. Its remarkable reasoning achievements signify OpenAI's progression to the second stage, Reasoner, in their 5-stage roadmap to artificial general intelligence, AGI. Now, if you haven't seen this, let me show it to you. These are the 5 stages of artificial intelligence according to OpenAI. So level 1, chatbots, AI with conversational language. We've accomplished that. That is essentially every large language model as we know it today. Level 2, reasoners, human level problem solving. That is what the paper is saying we're at now. However, in my opinion, we're definitely past that, and we're probably at level 3, if not verging on level 4. So level 3, agents, systems that can take actions. So we're almost there. It has been rumored that OpenAI is developing their own browser, for example. There are a bunch of agents that have been released lately that can take actions on your behalf. This is kind of already being explored right now. Then level 4, innovators, AI that can aid invention. And if you remember back to the situational awareness paper, that is the last step necessary before we hit artificial superintelligence. When an AI model can explore new science, new math, and then apply that to itself and self-improve, that is when we have the intelligence explosion. And level 5, full organizations run by AI. We are not there yet. So with that in mind, let's go back to the paper. And I specifically want to go back to test time compute. Remember, that is the thinking aspect of these models. So anytime I say test time compute, you think thinking. The blog and system card of O1 demonstrate that the performance of O1 consistently improves with increasing the computation of reinforcement learning and inference. Basically, the more time you give it to think, the better the result. This suggests that O1 could drive 2 paradigm shifts in AI, from self-supervised learning toward reinforcement learning, and from scaling solely training computation to scaling both training and inference computation. That is why I believe the biggest innovation, the biggest leap of 2024 in terms of AI was the O1 model. The O1 model showed that we have a new way to scale up. Now, previously, the training was the only thing we were scaling, basically feeding a model more and more data during training. However, we're basically out of data, publicly available data. Now, there's a whole ocean of data available behind authentication and paywalls, but those are not available to the public, thus they're really hard to train on. But now we can scale up something essentially infinitely because the thinking aspect doesn't require anything but compute. Now, I know a lot of this may seem very complex, but you know what is actually very simple? The partner of today's video. If you've watched this channel at all, you know I'm bullish on agents, and especially agents that can accomplish real-world tasks for you. That's why I'm excited to tell you about Emergence AI. Emergence AI just launched their enterprise-grade multi-agent orchestrator, and they showed off the first demo of a real-world use case where these agents can actually browse the web on your behalf. This is enhanced web automation. This means multiple agents can go out and dynamically interact with different elements on the web under this intelligent orchestration to bring human-like interaction and navigation, but at machine level scale. And what's really cool about this is these agents can actually perform complex and sophisticated web interactions that previously required a human. They can navigate dynamic early loading menus, fill out forms, adjust settings, process embedded files, and extract relevant data from PDFs and HTML. Emergence AI's orchestrator offers a combination of design time flexibility and runtime determinism. That basically means that these agents can heal themselves. So if it makes a mistake along the way, it can figure it out and then succeed on the next try. And Emergence AI has put a huge emphasis on privacy and security. They offer a fully hosted solution where you can access it via API, or you can host it on your own virtual private cloud. So if you're an enterprise business and you're looking to automate a lot of your processes, Emergence AI is a great solution. Integrate their agent API and seamlessly orchestrate multiple agents to accomplish tasks for you and your business. This includes interacting with both modern and legacy enterprise applications. So Emergence AI is just starting to invite developers to try out their platform. Definitely check them out. Tell them I sent you, of course. Go to their website, emergence.ai, or simply email them, contact@emergence.ai. I'll drop all of the links in the description below. So thank you again to Emergence AI for partnering with me on this video. Now, back to the video. All right, so what did these researchers discover? How do the thinking models work? Well, it can be broken down into 4 aspects. 1, policy initialization. 2, reward design. 3, search. And 4, learning. And don't worry, I'm going to break all of these terms down and explain exactly how they work. So policy initialization can be thought of as everything that happens before the prompt is actually submitted. And so policy initialization, you can kind of think of as the substrate of the large language model, the initial ingredients necessary to give it the ability to do everything else. So as we see in this graph here, here's the policy initialization, and it includes pre-training, so basically gathering all the data from the web and training a model. Instruction fine-tuning, which means giving it question and answer pairs to help guide the way it responds. And then human-like reasoning behaviors, which allows the large language models to behave like humans do kind of intuitively. Things like goal clarification, task decomposition, alternative proposals, solution generation, self-evaluation, and self-correction, all of which I'll go over. Next is reward design. Reward means how do you tell the model if it's doing something good or bad? So let's use chess as an example. AI that is trained to win at chess, the reward would be winning. So let's say the model would get a +1 every time it won and a -1 every time it would lose. That's a very basic explanation of how it works. But that is what is meant by reward. But with large language models, those rewards are kind of hard to come by. With fully enclosed games like chess, like Go, like video games where there's a very clear reward, that's great. But with language, it's not always clear. And so how that reward is designed is a big part of how these thinking models work. Next is search, which I believe is probably the most important factor to how these thinking models work. And search is done both at training time and at inference time. And remember, inference just means the time at which you prompt the model and it's giving you the result. Now, search during inference time is what O1 is really known for. And if you're ever able to look at the thought process of one of these thinking models, you'll kind of see that where it proposes a solution, maybe multiple solutions, tries to figure out which one is best, and then iterates on that one. And that's just one example of how it could work. And then last is learning. And specifically in learning, we're talking about reinforcement learning, which means the AI is interacting with its environment and learning along the way, rather than a human needing to tell it what's right and what's wrong. Now, human-based learning, where humans are telling it, is very expensive because humans are the bottleneck. Whereas reinforcement learning through interacting with an environment, there really is no bottleneck except for how much compute you can throw at it. So let's start with policy initialization. Let's break that down. So in reinforcement learning, a policy defines how an agent selects actions in response to environmental states. And there are essentially 3 levels that this can occur at. One is at the solution level, which is kind of the highest level. Then there's the step level, which is 1 step below that. So if you think about the solution as the overall solution to the problem, the steps that were taken to actually arrive at the solution is the next step down, so the steps. And then below that are the tokens, and the tokens build up to the steps build up to the solution. And so they go on to say for models like O1, incorporating human-like reasoning behaviors is crucial to enable more sophisticated exploration of solution spaces. They summarize 6 key behaviors that can be activated through prompts or learned through expert trajectories distillation from LLMs. So what are those 6 reasoning behaviors? These are things that humans do that we now need to teach a large language model to do. So here they are. I'm going to break them down for you. So first is problem analysis, which is exactly what it sounds like. The AI model takes its time to understand the problem and break down the problem before attempting to solve it. So if you go and buy some IKEA furniture, you don't just start building. You look at the instructions, and the instructions are broken down into step by step. And because of that, each step builds on the previous step. And that is an example of problem analysis. So the problem analysis can include multiple steps itself. So 1, explicit problem restatement to verify understanding, identification of implicit constraints, and transformation of abstract requirements into concrete actionable specifications. And this is good to think about while you're actually doing prompt engineering, because you can actually ask the model, hey, take a look at the problem and how I've stated it, and let me know if there are any clarifications that you need. Next is task decomposition. And so this is kind of the second step of the IKEA example. So first you analyze it and see how it could possibly be broken down. And then you actually do the breaking down step by step of building this piece of furniture. And so it's exactly what the large language models do with complex problems. When encountering complex problems, humans typically decompose them into several manageable subtasks. So for example, in coding tasks, O1 decomposes the problem into several subtasks, including capturing input strings, removing spaces, and parsing input strings. Then it's task completion. The model generates solutions through step-by-step reasoning based on clarified problems and decomposed subtasks. This behavior forms the foundation for all other reasoning processes. So again, we're just walking through how these thinking models have these human-like reasoning behaviors. Successful solutions lead to subsequent subtask processing. So if it finds a successful solution, they continue down that path, and problematic solutions or error solutions trigger the generation of alternatives or self-correcting behaviors. And here's the key, and something that if you've watched this channel at all, you already know. Step-by-step generation significantly enhances models' complex reasoning capabilities. Now, if you've seen any of my benchmarking videos, you know for most of them, I say, think through this step by step, because that's just a prompt engineering trick to allow the models to produce higher quality results. Next is alternative proposal. So when faced with reasoning obstacles or dead ends, the ability to generate diverse alternative solutions become crucial. O1 demonstrates this capability in cipher solving by systematically proposing several options. And one way to do that with very diverse potential options is by setting the temperature really high, which will produce varied results. Next is self-evaluation, and one of, if not the most important, in the ability for AI models to reason like humans. Now, one thing that I've said on this channel quite a bit is that models are much better at evaluation than generation. They are much better at looking at somebody else's solution and saying whether it's right or wrong and why, versus coming up with the correct solution themselves on the first try. That is why agents are so powerful, and agent collaboration in particular. When you have multiple agents working together, one can generate a response and the other or others can evaluate it and propose solutions. So that iterative cycle allows a much better response overall. And of course, on that note, self-correction is last. So when evaluating, if an AI model sees problems, it can propose fixes fix itself, and then retest. So in this next section, the researchers speculate as to how policy initialization is done with O1. So first, long text generation capabilities. During inference, LLMs need to generate a large number of tokens to encompass complex and diverse reasoning behaviors, which requires sophisticated long context modeling capabilities. For a while, that was a bottleneck of many models. The Gemini model has something like 2 million tokens now, which I think is the best in class. And the O1 models have plenty of tokens to work with, but that is a requirement to do any of these techniques, is that the context window needs to be sufficiently large. Now, here's something interesting that I didn't realize. Listen to this. Shaping human-like reasoning behaviors logically. Current research demonstrates that exposure to programming code and structured logical data significantly strengthens a model's reasoning capabilities. So just the exposure to code itself is enough to give the model much better logical reasoning. And then, of course, self-reflection, which we've talked about. Self-reflection just means generate something and then reflect on whether you think that's right or wrong and how to improve it. Next, let's talk about reward design. How are the models supposed to know whether their output is right or wrong? So here are the two examples of reward design that they provide. One is ORM, which is outcome reward, and PRM, which is process reward. And I'll break both of those down. It's very simple if you look at what's going on here. One is outcome reward. Basically, is the total output right or wrong? So take as many steps as you need, think through it as long as you need, and then you either get a right or wrong at the end of it. However, for complex problems, there might have been multiple steps that were done correctly before the final step or final steps that were done incorrectly, and thus the entire solution is incorrect. And that doesn't seem like the most efficient way to give feedback to the model. But that is where process reward comes in. In process reward, it actually rewards each step of the process. So if it got the first 4 steps right, we would give the model feedback that those 4 steps were right before finally failing on the final 2 steps. And that's what we're seeing here. So exact same question in both, and both of the solutions were incorrect, but incorrect in the same way. Now, the difference is it actually got the first 3 steps right before finally getting the 4th and 5th steps wrong. So in the PRM example, it gives feedback that these 3 steps are right, and thus it could try to fix the 4th and 5th steps rather than just thinking the whole thing is wrong, throw it all out. Now, let's talk about rewards from the environment. And this is a really important way to reward an AI model for either getting the right or wrong answer. So from a realistic environment first, and the example that they give here is coding. So let's say a model generates a script and you know what the output of that script should be. So if you can run the script in a compiler, give the output back to the model and allow it to know whether it got the answer right or wrong, that is a really good way to give a reward to that model in a realistic environment. But that's not always available. Let's read. While some environments can provide valid feedback, interacting with them to obtain the reward signal can be costly, or the feedback may not be available at test time. For example, during testing, we might not have test cases to validate whether a program generated by the LLM is correct. In such cases, a reward model is required to simulate the reward signal from the environment. So basically simulating what that compiler might output. And then last is from AI judgment. And this is very common. We've talked about it on this channel, LLM as a judge. So if one model or multiple models comes up with a bunch of different proposals for solutions, then another LLM as the judge, typically the most intelligent or the most capable model, will judge those responses and choose the best. And so those are the types of rewards that can be given from the environment. All right, so how do these researchers think that the O1 model is doing their rewards? Given that O1 could handle multitask reasoning, its reward model is likely to incorporate multiple reward design methods. For complex reasoning tasks such as mathematics and code, where responses typically involve long chains of reasoning, a process reward model is more likely to be employed to supervise the immediate process rather than ORM, which just makes sense. Given that O1 can be fine-tuned using few-shot examples, we suspect that it has a robust reward model trained on a large and diverse dataset spanning a wide range of domains. Now, this next part is extremely interesting and really shows the different opinions about how we are going to reach AGI. Now, it talks about a world model, and a world model means an AI that can essentially predict and simulate anything. So can that be done with language alone? Jan LeCun, the head of Meta's AI division, doesn't think so. Many others don't think so. But there are plenty, such as OpenAI, who do believe language alone can help us reach artificial general intelligence and a world model. Now, if language alone cannot help us reach a world model, what can? Well, many think video. Some works claim that a video generator is a world model since the video generator can predict the images in future time steps. So like Sora, for example. And Fei-Fei Li, famed AI researcher, is also using a more video-esque technique of creating a world model with World Labs, her new startup. So here, LeCun mentioned in a paper from 2023, also proposes a framework where world model do not need to predict the next state. Instead, they predict the representation of the next state, which is easier and more efficient than predicting an image. So they just talk a lot about what this world model might look like in this very brief paragraph. All right, now let's move on to the fourth step, search. This is the fourth factor in how to create a thinking model. So what does search actually mean? It means an AI model's ability to generate multiple results and search through them and different permutations of them for the correct answer. For LLMs, performing random sampling during generation has become a mainstream method to improve output quality. That even small models can outperform large models leveraging search. That's really important. This search function, really the thinking part of thinking models, is what allows even small models to perform as good as larger models. Search refers to the process of finding the correct solution through multiple attempts or strategic exploration based on certain guidance, such as rewards or heuristic rules. Now, according to the paper, we believe that search plays a crucial role in both the training and inference processes of O1, but if you've watched this channel at all, if you've been exposed to AI at all over the past few months, you probably already thought that. We will refer to the search during these two stages as training time search, so everything before the actual inference, and of course, test time search, which happens during inference, the prompting. O1 demonstrates that increasing compute during inference with more time spent thinking can continuously improve model performance. That was the big breakthrough. We argue that O1's way to think more can be seen as a kind of search using more inference time computation to find better answers. So how does it actually determine which search path to use? So it has a bunch of potential options, a bunch of potential solutions. How does it know which way to go? Well, first, self-consistency uses majority voting or weighted sums to choose the answer with the lowest uncertainty. Universal self-consistency extends this approach to free-form responses, enabling large language models to select the most consistent answer without task-specific constraints, basically coming up with a bunch of different potential solutions and finding the ones which are most consistent. Then there is self-evaluation, which is critically important. To improve model performance, self-evaluation aims to let models assess their own outputs. This is self-reflection, self-evaluation, whatever you want to call it, leveraging the assumption that evaluation is easier than generation, known as generator discriminator gap. I want to say that again. The assumption that evaluation is easier than generation. Now, it's an assumption according to them, but it seems like a no-brainer to me. I always seem to get better results after the model evaluates its own output first and then tries to correct itself rather than me just taking the first response. Here they talk about LLM as a judge, which basically just means LLMs create a bunch of different potential outputs and then a separate LLM judges it for accuracy or quality, whatever it is needed to be judged on. All right, so let's talk about different search strategies. Now, I mentioned the different hierarchies available. There is the solution level, there is the step level, and the token level. Now, these are the same three problems, same three outputs, but they are broken down in different ways. The solution level is exactly what it sounds like. It is searching through the total solution, whereas the step level searches through each step that led to the solution. So you can see right here, it says steps 1 through 3. That is the full answer. And then here, we're actually searching through, okay, what is the best step 1? What is the best step 2? And what is the best step 3? Then finally, we can even break it down further to the token level. So rather than the step, each token that builds up to the step can be essentially voted on or judged. They go on to talk about different search strategies, two being tree search and sequential revisions. I'm not going to go too deep into this section. Let me just tell you the high level. Tree search generates multiple answers simultaneously, acting as a global search that explores a broader range of solutions. Now, that is essentially what we're seeing here. Whereas sequential revisions refine each attempt based on the previous one, functioning as a local search that may offer higher efficiency. So it's the quality versus efficiency trade-off. So let me give you a few examples of tree search algorithms. First, best of n sampling. Generates multiple candidate solutions from the model, then selects the best solution via a reward model while discarding the rest. And by the way, all of these things can be accomplished with really good prompt engineering or putting some deterministic code around it. Basically, a lot of what makes up an agent. Next is beam search. So classic tree search algorithm that traditionally expands and prunes branches based on partial sequence probabilities, typically conducted at the token level. Then we have MCTS, Monte Carlo tree search. It is a look-ahead search algorithm used for making optimal decisions in large search spaces, which can choose actions based on their expected returns. Now, a lot of people think Q-star is based on Monte Carlo tree search, but most likely it's probably a combination of all of these different things. Now, here's why MCTS is so powerful. As simulations increase, the search tree grows, values become more accurate, and the action selection policy improves by prioritizing higher value children. So basically, the more you scale, the better the results, and that is always good. For sequential revisions, it primarily conducts the search by iteratively refining the previous answer. The key feature is that it generates improved answers based on reflections on previous answers or changes in the environment. So come up with a solution, reflect on that solution, improve the solution, and repeat. All right, so now we get to the cool part. What are these researchers' speculations of how search is done on O1? So train time search. During training, O1 is more likely to employ tree search techniques such as BON or tree search algorithms and primarily relies on external guidance. Test time search, so remember inference. For test time search, O1 is more likely to use sequential revisions, combining internal guidance to continuously refine and correct its search through reflection. So that's kind of what you see when you look at these models' chain of thought. Last, learning. How do we give the model the ability to learn from everything we've been talking about so far? What makes reinforcement learning essential is that the training data of reinforcement learning is unlimited, which comes from interaction with the environment. Now that's key. When you remove humans from the equation, you could scale up. But if you have RLHF, reinforcement through human feedback, that is a bottleneck. Human expert data is limited and expensive. Reinforcement learning has the potential to achieve superhuman performance since it learns from trial and error instead of human expert data. And they give a great example of it through AlphaGo. Now, AlphaGo was not trained on human data. It was basically given the rules of the game Go and allowed to play it a bunch of times, like a lot of times. And each time it figured out, okay, what was the optimal strategy of that game? Let me learn from that and discard the other one. And what that allows for is, as it says here, superhuman performance. And that is what we saw with the famed Move 37 when AlphaGo was playing the best human Go player in the world. On Move 37, everybody thought the AI made a mistake. Nobody had ever seen a move like that before with human players. But then later in the game, that was the critical winning move. So essentially, the AI discovered a new strategy for Go, and that is what is meant by superhuman performance. When you allow these models to explore the universe of possible moves on its own without the need for human feedback, it could find moves that were just not thought of by humans ever. And I find that absolutely fascinating. Now, the culmination of this paper is, how do you make an open source thinking model? How do you make an open source O1 or O3? The academic community has made available several open source implementations of O1. Now, obviously, they're not quite as good yet, but the fact that we have these techniques available and we have these open source projects means we're not that far behind. We have DeepSeek R1, QWQ, so there's a few of them. So G1, Thinking Claude, Open O1, O1 Journey. There are a bunch of them that you can play with right now. So now that we know with high confidence how O1 and O3 work, Where do we go from here? Well, the researchers highlight a number of future directions. One is, how do we adapt O1 to general domains? When there's a very clear answer like math or science, then it's easier. But when we don't know the answer, how do we do that? How do we allow these models to think through problems that we don't even know the answer to yet? Next, how do we introduce multiple modality to O1? That is something that I know OpenAI is working on because they've already talked about it. And then finally, how do we learn and search within a world model? So that will allow us to take this incredible intelligence and apply it to the real world, the real physical world. So that's it. I found this paper absolutely amazing to read, super interesting. I hope you enjoyed it as well. If you enjoyed this video, please consider giving a like and subscribe, and I'll see you in the next one.